Welcome to AI Frontiers. Today's episode, titled Silent Algorithms, Lasting Impact, explores 113 recent machine learning papers published on December 7, 2025. We'll examine how models silently influence decisions in areas like news, logistics, and healthcare, and why breakthroughs in fairness, efficiency, and trust are shaping our digital world. Join us for a deep dive into the evolving landscape of CS learning. In this episode, listeners can expect a guided tour through the latest machine learning research. The focus will be on uncovering the field's major themes, technical trends, and emerging insights as revealed across 113 peer-reviewed studies. Core ideas will be clearly explained, introducing pivotal papers that are reshaping approaches to model development, evaluation, and deployment. This journey will help envision the future of trustworthy artificial intelligence systems. Machine learning is the science of building models that learn patterns from data rather than following static instructions. This technology drives real-world applications, ranging from real-time language translation to advanced medical diagnostics, and sits at the intersection of statistics, optimization, data science, and artificial intelligence. As a central pillar of modern tools and societal systems, machine learning's importance is reflected in the vibrant research community found on the arXiv preprint server under CS Learning, where the latest advancements and debates are shared. Theme 1 centers on the interpretability and explainability of machine learning models. Understanding how a model arrives at its decisions is critical for building trust, especially in sensitive domains. Culling and colleagues use sparse autoencoders to reveal latent knowledge within chemistry language models, while Athreya and collaborators employ topological data analysis to map the internal reasoning of neural networks. These efforts strive to make artificial intelligence decisions visible and verifiable, highlighting the ongoing challenge of balancing model accuracy with transparency. The second major theme is the development of efficient and scalable model architectures. As datasets continue to grow in size and complexity, computational demands threaten to outstrip available hardware. Innovations such as Shahbazi's LUDA, which implements scalable and accurate linear attention, and Lu's-gated FWA, which introduces memory-efficient sequence modeling, are designed to address these limitations. Advances in linear attention mechanisms allow models to scale with sequence length, facilitating application to longer and more complex data without prohibitive computational costs. A third critical theme is the focus on fairness, robustness, and unlearning in machine learning. Papers by Lu and collaborators introduce methods like Learn and Recover to Forget, which enable selective unlearning to remove specific knowledge for privacy and regulatory compliance. Addressing and mitigating model bias, especially in graph-based architectures, is highlighted as essential for positive societal impact. Prioritizing robustness to bias and privacy violations is a key aspect of building trustworthy machine learning systems. The fourth theme covers reinforcement learning and time series forecasting. Park and colleagues demonstrate that using action chunks can significantly improve the scalability of offline reinforcement learning. Yang's work introduces frequency-based models that enhance time series accuracy, while Gopali and team leverage large language models to forecast temporal data. Reinforcement learning agents now learn efficiently from existing datasets, and frequency domain analysis is employed to uncover hidden temporal patterns, improving predictive performance across various domains. Key findings from this comprehensive review include several pivotal advancements. Collett's group establishes balanced accuracy as a crucial metric for fair evaluation of models and annotators. Park's introduction of action chunking enables robust and scalable reinforcement learning. Yagokar and colleagues promote transparency by training language models to produce confessions, increasing honesty in AI outputs. Shahbazi's linear attention mechanism advances long sequence modeling, and Ding's clarity model sets new standards for interpretable clinical artificial intelligence. Each of these contributions addresses core challenges in fairness, honesty, scalability, and domain-specific interpretability. Progress in machine learning is propelled by a range of methodological innovations. Deep neural networks, particularly transformer-based architectures, remain foundational due to their capacity for learning complex patterns. Luna's linear attention mechanism demonstrates how computational efficiency can be improved without loss of accuracy. Model-based reinforcement learning enables agents to use internal models for planning, akin to strategies used in chess. Techniques such as sparse autoencoders, topological data analysis, and prototype-based networks enhance interpretability. For fairness and unlearning, LoRa adapters facilitate targeted knowledge removal, supporting privacy and compliance objectives. Kalata et al.'s paper, Balanced Accuracy, the Right Metric for Evaluating LLM Judges, explained through Unlearning's J statistic, addresses the critical issue of evaluation metrics for classifiers, particularly in contexts such as language model judges and human annotators. The authors present balanced accuracy derived from Unlearning's J statistic as a robust alternative to traditional metrics like accuracy and F1-SCORE, especially in imbalanced or arbitrarily defined classification tasks. Their empirical and theoretical analysis demonstrates that balanced accuracy delivers unbiased and reliable prevalence estimates, which is vital for trustworthy model selection and applications, including content moderation and medical diagnosis. This work is recognized for its foundational impact on rigorous and fair evaluation practices in artificial intelligence. The paper by Park and colleagues, titled Scalable Offline Model-Based RL with Action Chunks, introduces a breakthrough in reinforcement learning for long-horizon tasks. The central innovation is the use of action chunks, predicting the outcomes of sequences of actions rather than single steps to reduce error propagation in offline settings. This approach enables practical reinforcement learning on large-scale datasets by minimizing the number of model simulations required. The method, referred to as Model-Based RL with Action Chunks, or MAC, achieves state-of-the-art results on tasks with up to 100 million transitions. The significance of this work lies in its advancement of RL scalability and reliability, paving the way for deployment in complex real-world domains. Jogokar et al.'s paper, Training LLMs for Honesty via Confessions, presents an innovative approach to fostering transparency in large language models. The method involves training models to generate confessions after providing an answer, explicitly reporting any errors, misbehaviors, or deviations from instructions. The reward structure incentivizes honesty in these confessions, independent of the correctness of the main response. Experimental results show that models trained with this method, such as those based on the GPT-5-THINKING architecture, are significantly more likely to self-report errors, enhancing oversight and user trust. This technique is especially relevant for safety-critical applications, where transparency and accountability are paramount. Looking ahead, several emerging challenges and opportunities are shaping the future of machine learning. Hybrid models that integrate logical reasoning with deep learning are expected to improve transparency and interpretability. Efficiency in computation and the capacity for dynamic unlearning will become increasingly important for sustainability and regulatory compliance. The incorporation of causal reasoning will enable models to understand interventions rather than merely recognizing patterns, thus supporting more robust decision-making. Domain-specific foundation models are poised to transform areas such as healthcare and climate science. Ultimately, real-world impact and ethical alignment will drive the next wave of advances in artificial intelligence. This presentation was synthesized using advanced artificial intelligence tools. Summaries and narrative structure were generated by GPT 4.1 from OpenAI, with TTS support provided by DeepGram and visuals by Grok. All content underwent expert human review to ensure accuracy and quality. Please note that some minor oversights may remain, so consulting the original referenced papers is recommended for in-depth study. All cited works are available for further reading on the arXiv preprint server. Thank you for joining us at AI Frontiers. If this research inspires you, consider subscribing to stay updated on the latest in artificial intelligence. Visit our YouTube channel, AI Frontiers, to engage with the community, share your insights, and help shape the future of AI. Like, comment, and share your favorite findings. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.